Hello everyone. I, Subramanya Hegde, working as Assistant Professor in the Department of Electrical and Electronics Engineering, KLS VDIT Halia, welcoming you all for the lecture series on Utilization of Electrical Power. Subject code is 17EE742 for 7th semester, module number 4 and lecture number 31. Today I am going to explain the series parallel control of traction drives, that is bridge transition method and shunt transition method. And we are also going to solve the numerical examples on series parallel control of traction drives. The learning outcomes after this lecture, the student will able to understand the traction motor control, that series parallel control. Again, in series parallel control, two types, shunt and bridge transition method. In previous class, we studied the concept of series parallel control. We considered two series motor. Normally, series DC series motor is employed in traction work because it produces large torque, large starting torque. When two motors are connected in series, okay, initially the two motors are connected in series. The current flows through the both motors are equal. Okay. Initially, the starting resistance is inserted in order to limit the starting current. Electrical supply is applied to starter, it is resistance starter, primary resistor. Okay, resistance value is large during the starting. Gradually, the resistance is reduced. Initially, the back EMF produced from the DC series motor is 0. When supply is applied, back EMF produced is 0. Gradually, the starting resistance is reduced. Voltage drop across the starter reduces. Initially, it is high. Okay, motor gradually increases the back EMF production. Back EMF increases, mechanical output also increases. When the two motors achieve the same speed, okay, the supply voltage is equal to half of the back EMF produced. The back EMF produced plus losses in the two motors. Back EMF produced is half of the supply voltage plus IR drop of each motor. In order to achieve high speed, the two motors are connected in parallel. When two motors are connected in parallel, the current is divided into two parts. In previous case, in series condition, only I flows through the circuit, now 2I. Again, the resistance is inserted, supply is applied through resistor. Okay? And when motor reaches to its maximum speed, the motor speed can be controlled with the help of field diverting method or any other method. We studied the series parallel control with the help of graph. Okay. We also find the efficiency for the starting. The efficiency of starting by series parallel method. Here it is clearly shown that the shaded portion is voltage drop across the starter. When supply is applied, this white portion is back EMF. When supply is applied, back EMF is 0. Full voltage is applied across the starter. Starting resistance is gradually reduced. When it comes to the 0 position, back EMF production is maximum. Okay, so voltage drop across the resistor is inversely proportional to the back EMF produced in the motor. So this is series operation. O to E is the time required for series operation. When motor is switched on to series to parallel mode, again the resistance is reinserted. Okay, this much voltage drop comes. So now we need to find the energy loss across the starter. As we know, OE is equal to EH in this diagram. So OE is time required for series operation, EH is time required for parallel operation. TS plus TP is equal to T. Okay, so here we can say TS is T by 2, TP also T by 2. The total time OH is equal to T. The average starting current will be I per motor, capital I. The energy lost in the starter is during the series period, energy loss during the series period, energy loss during the parallel period. Consider the triangle OKC and DCF. OKC, the area under the OKC is related to the energy loss during the series operation. Area under the triangle DCF related to the energy loss during the parallel operation. As we know, the area of triangle is half BH, height is V, and base is T by 2. So both case T by 2, height is V, and this is V by 2. So half VI into T by 2. Okay, T by 2. We are multiplying I because we are calculating energy loss. Voltage into current into time is energy. Anyhow, it is a DC circuit. Okay, power factor is 1. Next, voltage, parallel operation, current doubles. Okay, voltage is V by 2. In series operation, full voltage V is considered. Okay, in parallel operation, half voltage is V by 2 is considered. Current is 2I. So finally, we got VIT divided by 2. The total energy supplied, this is the energy lost across the starting resistance is VIT by 2. Total energy supplied is VIT by 2 plus V into 2I into T by 2. Parallel operation, series operation, VIT by 2. Parallel operation, VIT. Okay, VIT. Totally we got 3VIT by 2. This is input and this one is output. The efficiency of the starting is VIT by 2 minus VIT by 2, that is output, divided by input. So this is the energy lost, where the total energy supplied is input minus output. Input minus losses is output. So this input is 3 VIT by 2, where loss is VIT by 2. Okay. So finally we got 66.666%. The efficiency of the starting is 66.666. It's 2 by 3. So as we know, initially the two motors are connected in series. Later it is connected to parallel. Initially more torque is required in order to overcome the inertia. Then in order to take the load, two motors are connected in series. Okay. In order to shift the motor from series operation to parallel operation, shunt transition method is used. This is starting resistance, the field of the first motor, armature of the first motor, field of the second motor, armature of the second motor. There are totally 8 stages are shown. Stage 1, 2, 3 and 4 related to the series position. 5, 6, 7, 8, where 5, 6, 7 is shunt transition stage and 8th one is full parallel operation. You see the working of shunt transition method. In order to limit the starting current, primary resistors are inserted. Okay. In the first stage, the two motors are connected in series. Uh, Output of the one motor, that is negative of the one motor is connected to positive of the another motor field. Okay, then it is connected to the supply. Electrical supply is applied through starting resistance. Gradually resistance reduced. Okay, value of the resistance is reduced. In the first stage, it includes 100% resistance, starting resistance. In the stage 2, the next step, the resistance is reduced. In stage 3, resistance is still reduced. The voltage across the motor increases, back EMF production increases, motor speed increases. At stage 4, okay, the starting resistance is completely bypassed. Full voltage is applied to the series combination, and the motor gives one speed. The two motor gives one speed. Okay, voltage is equal to back EMF plus back EMF produced in the two motor, that is V by 2, plus IR drop of the two motors. Now motor is the electric traction device is started and it achieves one speed. In order to increase the speed of the device, these two motor is connected in parallel, not in a single stage. The very first stage is in the fourth stage, starting resistance is completely bypassed. In the fifth stage, some amount of resistance is retained in the circuit, so less voltage is applied to this combination. In the sixth stage, the one motor is completely bypassed, motor 2 is bypassed. Output of the motor 1, the output side of the motor 1 is directly connected to the supply, motor 2 is completely bypassed. Okay, resistance is included, it restricts the input. Next, seventh stage, again resistance is connected to the circuit only. Field of the second motor is disconnected, one of the motor field is disconnected. In the sixth up to fifth stage, the two motor produces the speed. In sixth stage, only one motor produces the speed. Speed of the device reduces, it causes jerking effect, vibration effect. In the seventh stage, stage 7, one motor is completely disconnected. Okay, here also speed of the device reduces. In eighth stage, the two motors are connected in parallel. Okay, two motors are connected in parallel, and this device gives full speed. Okay, or with the help of parallel connection we can achieve high speed. The main demerit of the shunt transition method is when it is switching from series to parallel operation. Okay, series to parallel operation, it introduces jerking effect. This jerking effect cause mechanical imbalance, vibration, inconvenience to the passenger, and it reduces the life of the bearings. In order to avoid this effect, in order to avoid the bypassing of a motor, in order to avoid the jerking effect, in order to increase the bearing life, the shunt transition method is replaced with bridge transition method. What is the bridge transition method then? In order to overcome the demerits in shunt transition method, bridge transition method is introduced. The bridge transition method, first one is series position, second one transition step, and the third one is first parallel position. Here, the two motors are connected in series only. Two motors are connected in series only, but in between, the starting resistance is included. Here, electrical supply is applied to the motor 1, then field and the starting resistance A, and A B to A dash is starting resistance, and A dash is connected to A with the help of linking pin, and A is connected to B dash. B dash is connected to motor, and motor back to the negative terminal of the supply. Okay. Motor is started and two motors are achieves one speed. Next one, transition step. In the transition step, resistance is inserted to the circuit, okay, inserted to the circuit, and resistance value is fixed. This link p, the link pin p is connected to the b to b dash, b to b dash, okay. Less amount of resistance is connected to the circuit. Now once the motor is connected in parallel, it's the first parallel position, link pin p is removed. In three steps, two motors, in all three steps two motor is connected to the circuit, okay. None of the motor is bypassed, so you can avoid the jerking effect, then we can increase the life of the bearings, okay, and we can provide good railway service. So bridge and shunt transition method is most widely used in series parallel control of traction device. We show a numerical example related to the shunt and series transition method. A motor coach bogie having two series motor is accelerated uniform to a speed of 45 km per hour in 25 seconds with the help of series parallel controller. If the average tractive effort, if the average tractive effort per motor is 1 lakh 12,750 Newton, calculate the approximate loss of energy in the starting rheostat. The maximum speed attained by the train is 45 km per hour. It's converted into meter per second, 12.5 meter per second, where t is 25 second. Total ft is, two motors are there, so 2 into 12,750, so 25,500 Newton. Useful energy for acceleration. The useful energy for acceleration is half into ft into v, okay, half ft into v. If it is in kilometer per hour, where power is ft into v, multiplied by time, it's energy, power into time, energy, so time in seconds converted into hours, 3600. So on the half into 25,500 into 12.5 into 1 by 1000 into 25 divided by 3600, 25 second is converted into hours. Finally we got 1.107 kilowatt hour. The loss of energy in the starting rheostat is approximately equal to the half the useful energy, so it is 0.5535 kilowatt hour. The next problem, the two motors of a motor coach are started in series parallel system. The current per motor being 350 amperes considered as being constant during the starting period, which is 18 seconds. If the acceleration during the starting period is uniform, the line voltage is 600 volts and resistance of each motor is 0.1 ohm. Calculate the time during which the motor are operated in series. Ts we need to find. The energy loss in the rheostat during the starting period. As per the problem definition, current per motor is 350 ampere, that is I, and time, total time is 18 seconds. Supplied voltage is 600 volts and resistance is 0.1. The time during which the motor operated in series, that is Ts, is equal to half V minus 2 IR divided by V minus IR into T. Now we are going to substitute the values in the Ts formula. In the place of V 600, I 350 and R is 0.1. So Ts we got 8.44 seconds. Time required for series operation is 8.44 seconds. Time during which the motor are in parallel. Total time is series time required for series operation plus time required for parallel operation. Parallel operation time is T minus Ts. Here we got 9.56. The energy loss, the energy loss in the rheostat during starting period. First, we need to find the back EMF in order to calculate the energy loss. So back EMF of each motor in series operation is back EMF EB is equal to V by 2 minus IR. So here we got 265 volts. When two motors are in series, the back EMF is 265 plus 265. So that is 530 volts. The back EMF of each motor in parallel operation EB minus IR, EB is equal to V minus IR. So 600 minus 350 into 0.1565 volts. Energy lost when motors are connected in series. Back EMF into current into time required for series operation half EBITS. Here we got 217.4 watt hours. Energy lost when motors are connected in parallel, it's half EB by 2. The voltage taken is VB by 2 and current taken is 2I into TP. After substituting all the values, 262.6 watt hours. Next one, a multiple unit train weighing 200 tons is equipped with 6 motors giving a total tractive effort of 82,800 Newton. The motors operated at a line voltage of 600 volts and each motor takes an average current of 200 ampere during the starting. The series parallel control is used for starting. The full line voltage is applied to each motor when the speed reaches to 38.6 km per hour. Resistance of each motor is 0.1 ohm. Calculate energy supplied during the starting period, energy lost in the starting resistance, useful energy supplied to the train. Total weight of the train is 200 total mass of the train is 210 mass, 10 tons. Number of motors 6. Tractive effort is 82,800 newtons. Line voltage is 600 volts. Current taken by each motor is 200 ampere. Voltage is 38.6. Velocity is 38.6 km per hour and resistance is 0.15 ohm. Energy supplied during the starting period is tractive force required is 277.8 m alpha, okay, where alpha is equal to ft divided by 277.8 into m. Here we got 1.42 km per hour. The time for acceleration is velocity divided by alpha 27.2 seconds. We know that ts is equal to, in order to find ts we require t, so initially we calculated t by calculating alpha. ts is equal to half v minus 2ir divided by v minus ir. Okay, after substituting the values, v is 600, I is 200, r is 0.15 and t is 27.2 seconds. Here you got 12.9 seconds, where tp is 14.3 seconds, t minus ts. The energy supplied is equal to energy supplied minus series position. The energy supplied in series position, two motors in series with three such circuits in parallel, plus energy supplied in parallel position, all motors in parallel, 3, considering 3 motor, 3 into 600 into 200, 12.9, 6 into 600 into 200 into 14.3. Okay, 3 motors, each motor takes 600 volts and 200 ampere current, and time required is 12.9. Finally, we got 4.15 kilowatt hour total energy supplied. Energy lost during the starting resistance is, in series position, it is 3 into half into 540 into 20, 540 into 200 into 12.9. Here we got 2.09 megawatt hours. Parallel operation 6 into 150 into 200 to 14.3. It is 2.57 megawatt hours. The total energy lost. Okay, total energy lost is energy lost during the series position, energy plus energy lost during the parallel position. Finally, we got 1.3 kilowatt hours. So energy lost in the motor resistance 0.272 kilowatt hours. The useful energy supplied to the train is useful energy is half FTV into T, half into 82,800, where velocity is converted into meter per second 38.6 into 1000 divided by 3600 into 1 by 1000, 27.2 divided by 3600 kilowatt hours. Here it is shown the IR is 30, it's 570 volts, and it is 60 volts IR drop in series position and 540 volt loss during the starting period. Here we got the answer 3.35 kilowatt hours. From this lecture we can conclude that shunt transition and bridge transition method is used in series parallel control. The main demerit in the shunt transition method is one of the motor is bypassed when it is switched from series to parallel operation. It reduces the speed of the train. It creates jerking effect. In order to overcome this effect, bridge transition method is employed. The series and shunt transition method explanation comes under understanding, and numerical example comes under apply level. These are the reference books. Thanks for watching this video. Thank you one and all.